Walk down any street, open any news app, scroll through social media, and you are absolutely bombarded with statistics.
They're everywhere, aren't they? Numbers about the economy, health trends, political polls, how effective some new product is.
Exactly. And they land in front of us, often feeling like objective truth, like hard facts in a messy, confusing world.
And statistics are incredibly powerful tools. I mean, for understanding the world, they're essential.
Mm.
But like any powerful tool, they could definitely be misused.
Yeah, sometimes intentionally, sometimes maybe not, but often in these subtle ways that can seriously twist the truth.
Totally. And that's really why we're diving into this topic today. We're not just here to look at numbers themselves. We're here to understand the mechanics, like how numbers can actually be used to mislead us.
Right. And our main source material for this deep dive is a real classic Darrell Huff's book, How to Lie with Statistics. It came out way back in 1954, believe it or not. It's still so relevant, though. And we're also looking at some related articles that dig into key ideas, especially that crucial difference between correlation and causation.
So our mission today really is to arm you with the knowledge and, well, the tools to look past the shiny numbers and start asking the right questions.
Think of it as gaining a kind of statistical self-defense. It's a good way to put it. So you can navigate this data-saturated world without being so easily fooled.
We're going to unpack some subtle and, yeah, sometimes pretty blatant ways statistics can twist reality.
And honestly, understanding these tricks is probably more important now than it's ever been with the sheer volume of information flying around.
Okay, so let's dive in. Where do we start?
Well, the absolute foundational concept, the thing you have to grasp when dealing with stats, especially when someone's trying to convince you one thing causes another, it's the difference between correlation and causation.
This feels like Statistics 101, maybe, but it's amazing how often this basic idea trips people up in the real world. It is fundamental, but easily forgotten. Correlation just means two things, two variables, tend to move together somehow. As one changes, the other tends to change too. There's a relationship.
Okay, they move together.
But causation is much stronger. It means one variable actually causes the other thing to happen. There's a direct mechanism, a link.
And the crucial point, the one Huff and everyone hammers home is...
Correlation does not imply causation. Cannot stress that enough. Just because two things happen together or seem related doesn't mean one caused the other.
Right, so why isn't correlation enough? Why can't we just say, okay, these track together, must be cause and effect?
Well, sometimes it is just random chance. The numbers happen to align in your particular data set purely by coincidence. Doesn't happen often with big data, but it can.
Okay, chance is one reason.
But more commonly, there's often a third factor, something unseen, or what statisticians call a lurking variable. And this lurking variable is influencing both of the things you're looking at.
Making them look related, even if they aren't directly causing each other?
Exactly. It creates a false connection.
Can you give us an example of that lurking variable idea from the sources?
Sure. One source uses the example of finding a positive correlation between exercise and skin cancer.
Wait, exercise and skin cancer, that sounds completely wrong.
It does. The data might show people who exercise more also tend to get skin cancer more often. If you just saw that statistic without thinking, you might leap to the, frankly, alarming conclusion that exercise causes cancer.
Which goes against everything we generally believe about health benefits of exercise.
Right. But the likely lurking variable there, exposure to sunlight, people who live in sunnier places might exercise more outdoors, and they also have higher rates of skin cancer because of the sun.
Oh, okay. So the sun exposure is affecting both the exercise habits, being outdoors, and the cancer risk. It's not the exercise itself.
Precisely. The sun is the hidden link influencing both variables.
Okay, that makes perfect sense. Another example you mentioned from the sources involved health data again, something about heart disease.
Yeah, finding correlations like increased heart disease associated with higher fat diets, that's a positive correlation. And then maybe increased exercise associated with less heart disease, a negative correlation.
Okay, those sound more intuitive, maybe.
They do. And look, those correlations might strongly suggest an underlying causal relationship. And in those specific cases, a lot of further research did eventually show causal links.
But the correlation alone wasn't proof.
Exactly. Just observing that trend in the data doesn't scientifically establish cause and effect. To do that, you need much more robust, well-designed empirical research.
Things like controlled experiments, randomization.
Yes, where you actively manipulate one variable, like diet or exercise, while trying to control for all the other factors. You can't just passively observe data where a million things are happening at once and claim causation.
Got it. So correlation is like a smoke signal. Might mean there's a fire, causation, but it could also just be, smoke. You need to investigate further.
Perfect analogy. It's a starting point, a flag, but absolutely not a conclusion on its own.
Okay, so if confusing correlation and causation is one big pitfall, what are some of the other ways statistics get twisted? This is where Huff comes in, right?
This is where Darrell Huff's book, How to Lie with Statistics, is just brilliant. Published in 1954, but the ways people misuse stats, fundamentally the same. The tricks are timeless, even if the data changes.
And it's interesting that he wasn't actually a statistician, he was a journalist.
Right, which I think is why the book is so accessible. It's written with such clarity and, frankly, wit. He uses really clear, relatable examples.
And his goal wasn't to teach you how to do statistics.
Right.
It was more defensive.
Exactly. It was to show you, the average person, how statistics can be misused and manipulated so you can spot it happening. He uses this great analogy.
The burglar one.
Yeah, like a burglar explaining how houses are broken into. Not to encourage burglary, obviously, but so homeowners know the weak points and can protect themselves.
That's such a good way to think about it, protecting yourself from misleading numbers.
And his core idea is that statistics themselves, the numbers, aren't inherently liars. They're just numbers from data. But the way they're gathered, the way they're presented, how they're interpreted, that's where the deception often creeps in.
He coined that term statisticulation, didn't he?
Yes. Statisticulation, the art of using numbers selectively, or maybe out of context, to push a certain narrative, making them look impressive while hiding the real story.
Like a secret language, one source called it, used to sensationalize, inflate, confuse, oversimplify.
And statistics can be technically true, using accurate numbers, but still be completely misleading about the reality. Accurate numbers, but maybe totally irrelevant to the point being made.
So let's get into the specifics. What are some of these common tricks Huff identified that we still see all the time? First up, the sample with the built-in bias.
Ah, yes. This is maybe the most fundamental vulnerability. The problem happens when the group you actually study your sample isn't really representative of the bigger group, the population you want to talk about.
And why is that so misleading? It sounds technical, but what's the impact?
Because it gives you what Huff calls a spurious air of scientific precision. You get a fancy number, maybe a chart, but it might be less accurate than just guessing if the sample is bad. It looks authoritative, but it's built on shaky ground.
Huff's classic example here is the Yale class of 24 income thing, right?
Yes. Years after graduation, a report came out saying their average income was something like $25,111 back then, which is a huge amount of money at the time. Sounds impressive.
Yeah, sounds like Yale grads were doing incredibly well. But what was the catch? Who is that average based on?
Well, almost certainly only those alumni who actually responded to the survey. And think about it. Who's likely to respond to a survey asking about their income years later?
Probably the ones who are doing well, right? Proud of their success, easy to find, willing to share.
Exactly. The ones who were maybe struggling or had fallen off the map or just didn't want to share, they're simply not in the data. The sample wasn't random. It basically selected itself, and it was heavily biased towards the successful ones. That skewed the average way up.
And sample bias isn't just about who responds. You mentioned other ways it creeps in.
Oh, yeah. Sources talk about people, maybe not telling the truth about sensitive topics, or maybe they misunderstand a complicated question, or even the interviewer's presence or characteristics influencing the answers.
Like that old study about race and attitudes towards the war, where the answers change depending on the interviewer's race.
Exactly. Subtle influences, but they create bias. So when you see a statistic from a study or a survey, the critical question is, who was actually in this sample? And just as vital, who was left out? Does this group truly reflect the larger group they're making claims about?
Okay, so the sample is crucial. But even if you get a decent sample, the way you summarize the data matters too. Which brings us to the next trick, the well-chosen average.
This is a great one because average sounds so simple, so definite, but it can mean very different things. Mean median, mode, they're all types of average.
And depending on which one you pick, you can paint a totally different picture using the exact same set of data.
Absolutely.
Yeah.
And someone with an agenda, whether it's a statistician or, an advertiser, can easily just pick the average that best suits their argument.
So the mean, adding everything up and dividing, that's a common one, but it's the one that gets skewed easily.
Very easily skewed by outliers, those really high or low values. The median, on the other hand, is the actual middle value when you line everything up. It often gives you a better sense of the typical experience, and the mode is just the most common number.
Huff's example was about buying a house, right, in a neighborhood with a high average income.
Yeah. If that reported average is the mean income, it could be skewed upwards by just a couple of super wealthy households, a few billionaires move in, and suddenly the mean shoots up.
But the median income, the middle household's income, might be much, much lower. That gives you a more realistic picture of what most people there actually earn.
Exactly. And you see this dramatically in national wealth statistics. One source highlights the huge gap between the mean household net worth in the U.S., pulled way up by the ultra-rich, and the median household net worth, which is far lower.
So the mean is technically correct, but practically misleading about how the typical family is doing. Shows inequality really starkly.
Perfectly. So the key question whenever you hear average is, which average are they using? Mean, median, or mode? And why do they choose that one? Does it represent the typical case, or is it being distorted by extremes?
Okay, let's move to another shady tactic. The little figures that are not there.
Ah, yes.
Yeah.
This is all about omission, leaving out crucial bits of information that would actually allow you to judge the statistic properly.
And leaving them out makes weak stats seem stronger than they are.
Totally. The classic example Huff uses is the toothpaste ad claiming something like, tests prove our toothpaste results in 23% fewer cavities.
Wow, 23% sounds so precise, so scientific.
It does. But Huff points out, and this still happens, that claim might be based on a ridiculously small study, maybe just, say, 12 people.
12 people, that's tiny.
Exactly. With a sample that small, finding slightly fewer cavities in one group could easily just be random chance.
Yeah.
What we talked about earlier, correlation by chance, it might have nothing to do with the toothpaste actually working.
So the sample size is one of those crucial little figures that often goes missing from the headline.
Absolutely critical. Like that early polio vaccine study mentioned in the sources, the initial sample was just too small to draw any firm conclusions compared to the control group. Without knowing the sample size, or maybe the margin of error.
Margin of error.
Yeah, the plus or minus range that tells you how much uncertainty there is around the number. Without that context, a statistic is far less meaningful, even if the number itself was calculated correctly from that tiny, potentially meaningless data set.
Okay, another related trick seems to be focusing on differences that are real, but maybe not important. Much ado about practically nothing.
Yes, this is about hyping up tiny differences that aren't actually statistically significant, or just don't matter in the real world, but presenting them as if they're major findings.
Can you give an example?
Think about IQ scores again. Say one kid, Peter, scores 98, and another, Linda, scores 101. Seems like Linda's clearly smarter, right? 3 points higher.
Looks like it on the surface.
But IQ scores, like most measurements, have a margin of error. Let's say it's plus or minus 3 points, just for argument. Peter's real score could be anywhere from 95 to 101. Linda's could be 98 to 104.
Ah, so their possible ranges overlap quite a bit.
Significantly. That 3-point difference between their reported scores is likely just statistical noise within the margin of error. It's probably not a meaningful difference in their actual intelligence, but someone could still advertise, children using our amazing products scored an average of 3 points higher on IQ tests.
Right. And the sources mentioned that old gold cigarette campaign from way back.
Yeah, Huff talks about that. They made a huge deal in their ads about having a tiny bit less nicotine or tar or something than competitors. A difference so small it was statistically insignificant and had zero real health impact, but they built this massive ad campaign around it.
So the question here is this difference actually meaningful? Does it matter in practice? And again, what's the margin of error?
Exactly. Always ask if the difference is big enough to care about.
Okay, speaking of ads and presentation, the gee whiz graph. This sounds fun. It's about visual manipulation.
Totally. Graphs are supposed to make data easier to understand, visualize trends, but they are so easy to manipulate, to distort reality, make tiny changes look enormous and dramatic.
Yeah.
The goal is to get that gee whiz reaction.
And the most common way is messing with the axis, the scale.
Yes, especially the vertical axis, the axis. The sneakiest trick is truncating it, basically, chopping off the bottom so the scale doesn't start at zero.
How does that work?
Well, imagine a company's profit went up just a little bit. If you plot that on a graph that starts at 0, the line might look pretty flat, unimpressive. But if you cut off the bottom and start the graph near the lowest point of the data,
Then that small increase suddenly looks like a steep climb.
Exactly. A skyrocketing spike. Huff uses a great example of a Newsweek stock price graph from the 50s that did exactly this.
Huh.
Made a modest rise look incredibly dramatic.
What about using pictures instead of bars?
Ah, the pictogram trap. Like using little drawings of money bags or people to represent quantities. If you want to show that income doubled, you might draw the second money bag twice as tall.
Seems logical, twice as tall, twice the money.
But visually, it's misleading. Because when you double the height, the area of that 2D drawing on the page becomes 4 times bigger.
Yeah.
And if you imply volume, like a 3D bag, doubling the height makes the volume 8 times bigger.
Wow. Okay, so visually it exaggerates the difference hugely.
Massively. So the lesson is, always look very carefully at a graph scale. Does the vertical axis start at 0? Are the proportions accurate? Is it showing the data honestly? Or is it deliberately crafting a sensational but misleading story?
Good advice. Okay, next up, the one-dimensional picture. This is about oversimplification.
Yeah, it's the problem of taking a really complex situation, something with many facets, and boiling it all down to just a single number.
Like a company boasting, we cut costs by 20% last year.
Right. That 20% figure might be technically accurate from their accounting books, but it's totally one-dimensional. It tells you nothing about how they cut costs.
Did quality plummet because they used cheaper materials? Did they fire half the customer service team? Did employee morale tank?
Exactly. Did they just push maintenance costs into the next year? That single number hides all the crucial context, the nuances, the potential negative trade-offs. It's accurate, but incomplete.
Or the classic average family has 2.3 children example.
Yeah, that's a true mean average, total kids divided by total families. But it completely hides the reality of the distribution. Most families might have 2 kids, or 1, or 3. A few large families pull that mean up.
So the single number doesn't actually describe the typical family experience well at all.
Not really. The key question with these single figures is, what else do I need to know? What context is missing? What other numbers would give me a fuller picture?
Okay, this next one sounds really sneaky. The semi-attached figure.
It is pretty sneaky. This is where someone presents a statistic or maybe a visual that looks relevant and authoritative, but it actually has very little or maybe even no real logical connection to the claim they're making.
So it's like trying to borrow credibility by association.
That's a perfect way to put it. They show you an impressive-looking number or chart, hoping you'll subconsciously link it to their main point, even if there's no real bridge between them.
Like showing a picture of a happy, smiling family next to a graph about falling food prices.
Exactly. It implies the family is happier because food costs less, but there's zero evidence connecting that specific family in the photo to those specific cost reductions, or that food prices are the key to their happiness. It's just an emotional association.
Or maybe using a very scientific-looking graph in an ad for, say, a skin cream, but the graph doesn't actually represent rigorous testing of that specific cream.
Precisely. Just looks science-y and lends an air of credibility without actually providing relevant proof. The question to ask yourself is this number or visual actually relevant to the specific argument being made here? Or is it just window dressing designed to impress me or distract me?
Got it. And the last main trip you mentioned circles right back to where we started with correlation and causation. Post hoc rides again.
Ah, yes, the good old post hoc ergo propter hoc fallacy. Latin for after this, therefore because of this.
It's assuming that just because event B happened right after event A, then A must have caused B confusing sequence with causality.
Exactly. It's the correlation versus causation mistake applied to reasoning about events over time.
Like the funny example, I washed my car this morning and then it rained this afternoon. Therefore, washing my car caused the rain.
It seems obviously silly there, but people make this error constantly with more complex situations. A company launches a new marketing campaign and sales go up the next quarter. Did the campaign cause the rise?
Or was it maybe improving economic conditions? Or a competitor stumbled? Or seasonality?
Exactly. Lots of other possibilities. Or consider the finding that smokers tend to get lower grades in school. Does smoking cause lower grades? Maybe. But maybe the stress of doing poorly leads some kids to smoke.
Or maybe a third factor, like maybe how much someone prioritizes socializing over studying influences both their likelihood to smoke and their grades.
That's another great possibility.
Hmm.
And the Cornell women example we touched on earlier is a classic post hoc trap. Statistics in the 50s showed female Cornell grads were less likely to be married soon after college compared to male grads. The immediate post hoc assumption was, aha, going to a demanding college like Cornell hurts a woman's marriage prospects.
But the alternative explanation.
Is that the women who chose to go to a place like Cornell back then were perhaps already more career-focused and maybe less focused on immediate marriage compared to the general female population at the time. Their pre-existing priorities likely influenced both their college choice and their marriage timing.
So the college itself wasn't necessarily the cause.
Probably not the sole or even primary cause. The key question with any A happened then B happened claim is, are there other plausible explanations for this relationship besides A directly causing B?
So statisticulation, then, is really the overall art of using all these tricks together. Biased samples, misleading averages, dodgy graphs, missing info, semi-attached figures, post hoc reasoning.
Exactly. It's combining these techniques, consciously or unconsciously sometimes, to twist statistics to fit a narrative, make them say what you want them to say, often while maintaining this veneer of scientific rigor and objectivity.
That's the core danger, isn't it? It looks so precise and factual.
It is. And that's why knowing these potential pitfalls, knowing how statistics can lie, is just the essential first step to not being misled by them.
Which brings us perfectly to the most important part, the toolkit. How can you, the listener, actually talk back to a statistic, as Huff puts it, when you encounter one?
Right. Huff offers this really practical 5-question checklist. These are the essential questions to train yourself to ask almost automatically whenever you see a statistic being used, especially if it's supporting a strong claim or trying to persuade you.
Okay, what's first on the list?
Who says so? Always look for potential bias in the source.
Bias. Like what?
Well, conscious or unconscious bias. Is the source a company trying to sell you something by showing stats about its product? Is it a political group using poll data selectively? Is it a media outlet maybe hyping a story for clicks or viewers? The source's interests and motivations matter hugely.
And sources mentioned even simple things like how a region is defined can change stats like life expectancy. That shows how much the source's choices matter.
Absolutely. Definitions, framing, it all comes from the who. Okay, second question. 2. How does Haitian know?
This is about the methodology, right? The data collection.
Exactly. Question how they got the number. Was the sample biased? Did it select itself like those Yale alumni? Was the sample just way too small to mean anything? Was it collected improperly? Is the size of the reported correlation even meaningful in context?
Like that China census example, the population count changed depending on the purpose of the census because people responded differently based on whether they thought it was for taxes or famine relief.
That's a fantastic illustration. The how deeply affects the number itself. Third question, 3. What's missing?
This is looking for those little figures that are not there.
Precisely. What crucial information has been left out? We mentioned sample size and margin of error. What about the type of average, used mean, median, mode? They should tell you. If they claim something is X% better, well, better than what?
Right.
What's the baseline comparison?
The example of rising cancer death rates being misleading without the context of better diagnosis, better reporting, and people simply living longer, that fits here perfectly. Missing context changes everything.
It really does. Okay, fourth question. 4. Did somebody change the subject?
Change the subject. How does that work with stats?
It means asking if one thing is being reported or maybe implied as if it's another thing. Is a simple correlation being dressed up and presented as definite cause and effect? That's the post hoc fallacy again. Is the language being twisted, like using different definitions of average or using big percentages based on tiny starting numbers to sound dramatic?
Is the conclusion they're drawing actually supported by the specific number they presented?
That's the core of it. Are they subtly shifting from the data to a conclusion that the data doesn't fully support? And finally, number 5, maybe the most underrated check. 5. Does it make sense?
Just a basic reality check.
Yeah, use your common sense. Does this statistic and the claim based on it generally align with what you already know about the world? Does it feel intuitively plausible, or does it clash strongly with other facts or experiences? Does the level of precision seem maybe too good to be true for the type of data?
Those funny Reddit examples you found really drive this home. The average person has one testicle.
Technically true if you average males and females.
Or
For fewer than 2 legs if you average in people with limb differences. Or more than 2 nipples because a tiny fraction have more. Mathematically derivable means, but they don't reflect common reality at all.
Or Air Force One has taken off more times than it's landed. Technically true because the plane designation changes mid-flight.
Or that average U.S. president has been indicted on 2 felony counts. True only because one recent outlier drastically skews the mean for that very small group. These show how a technically correct calculation can be absurd or misleading if you don't apply that common sense filter.
So just because a number exists and is calculated correctly doesn't mean it reflects reality meaningfully or is being used honestly.
Not at all. You need that does it make sense? Check.
The source has also touched briefly on a couple of other tricky concepts. Simpson's paradox.
Right. Simpson's paradox is fascinating. It's where a trend or relationship appears in different groups of data but disappears or even reverses when you combine those groups.
Like the gender wage gap example. The overall number shows a gap, but it changes when you look within specific industries or experience levels.
Exactly. The aggregated statistic is true. Women on average earn less than men on average. But looking only at that aggregate number can be misleading about the complex factors involved, like industry choice, hours worked, experience discrimination, etc. You need to disaggregate the data to understand the nuances. Ignoring Simpson's paradox can lead to faulty conclusions.
And non-transitive paradox, like rock, paper, scissors.
Yeah, just because A beats B and B beats C doesn't automatically mean A beats C. Comparisons don't always transfer logically across a whole set. And using the right type of average matters too, like using the geometric mean instead of the simple arithmetic mean for things like calculating average investment returns over time. It gives a different, often more accurate picture for growth rates.
Wow. Okay, so the takeaway isn't to just become a total cynic and distrust all numbers, right?
No, definitely not. That would be throwing the baby out with the bathwater.
No.
Statistics are absolutely essential. We need them to make sense of complex information, to understand trends, to make informed decisions.
Got.
But by understanding how they can lie, by knowing these common tricks and distortions, you become much, much better equipped to figure out when they're being used more honestly and when someone's trying to pull a fast one. It helps you get closer to the actual truth behind the numbers.
Knowing these techniques gives you power, really. A way to push back, ask those critical questions, demand more clarity and context.
You've got Huff's toolkit now. You can talk back to a statistic.
So as we wrap up this deep dive, the main message is statistics are vital tools, incredibly powerful, but they can be easily misused, sometimes on purpose, sometimes just carelessly.
Right. But by understanding these common pitfalls, sample bias, misleading averages, visual tricks, the post hoc fallacy, missing information, and by applying Huff's simple but powerful checklist of questions,
Who says so? How do they know? What's missing? Did they change the subject? Does it make sense?
you can navigate this data-heavy world with a lot more confidence. You shift from being just a passive recipient of numbers to being an active, critical thinker trying to find the real story.
And maybe here's a final thought to leave you with. Think about how much of what we sort of accept as common knowledge or base our own choices on what we buy, our health decisions, our opinions on big societal issues. How much of that is influenced by statistics that might be misleading in some way, subtle or not?
Yeah, what's the cumulative impact of all that potential misinterpretation? Not just on us as individuals, but on public opinion, on policy, on the direction society takes. It's definitely something to think about.
Something to mull over until our next deep dive.